Now we're going to go from sarcomere to contraction. We built our sarcomere. This is muscle part 3. So the whole question becomes how? We had the calcium flooding the cell. We have the structure of the sarcomere. How do we put all of this together to get that excitation, action potential, contraction, actual movement connected through the calcium? Here's what happens. Calcium binds the troponin, which then moves the tropomyosin off the binding site, so myosin can now attach to the actin. And here's a picture. Okay, I realize I drew the picture on this one because I was trying to make it to show it, which I didn't think they had a good picture. So here we have troponins in yellow, troponin is in red, tropomyosin is yellow, actin is blue. I've made these little purple binding sites. I was trying to show it. So here we have the inactive form where tropomyosin is blocking all the binding sites. When calcium comes in, it shifts the troponin and the tropomyosin. So now all the little binding sites are free and the myosin can bind the actin. But wait, there's more. They drew this picture. It didn't have the myosin binding, which is why I'd done my picture, but this shows how calcium shifts the troponin. So, but first we have to make sure that the myosin's ready to go. We got the actin ready, but now we have to activate the myosin. And the way we do that is we have to have yet more ATP. This is one of the reasons why muscle activity burns so much energy and is good for burning calories. Is ATP is going to bind that ATP binding site on the myosin. If you need to remember, go back up to the slide where we had that head group that came like this, and we had the actin site and we had an ATPase site on that head. So the ATP comes in and it breaks the myosin. It's an ACE, it's an enzyme. It's going to break the ADP and PI. So ATP, triphosphate, now gets broken into diphosphate and the PI, but it doesn't let it go yet. It keeps both pieces in the active site with the broken molecule. Then it can bind actin, but let's go back to here. It cannot bind actin until it has this broken piece. If it's an empty binding site, it cannot bind actin. It has to have these two pieces attached. It's kind of an allosteric regulation so that it can bind to the actin. So skeletal muscle is all about allosteric. Calcium attached allosterically, myosin is activated allosterically. So myosin binds to the actin. We have this ADP-PI. This forms what is commonly called the cross bridge. And at this point, the myosin head moves the actin towards the middle. So if I have my myosin this way and my actin this way, I'm going to move it in towards the center, which means that the phosphate is going to be released. But then in order to release the actin, we need a new ATP. So this is the picture from the book. So you'll notice here on the myosin, we have that ADP-PI. So, and we have calcium here on the troponin. So the myosin can now bind actin. So the head rises up and binds the actin at that actin myosin binding site. In doing so, the PI, the inorganic phosphate, comes off. Because it comes off, that myosin now is pulled towards that center, pulled in towards the center of the sarcomere. And when that happens, we now release the ADP. So we release the PI when we attach, we release the ADP when we move. We're now in the move state. We're stuck. This is static, right? It's now in the move state. Now I have to add a brand new ATP in order to come off. If for whatever reason the body runs out of ATP, this stays in the stuck contracted position. That's what rigor mortis is. After you die, you run out of ATP, the muscles contract and cannot relax. Here we have a new ATP. we have to break it down to start the whole process over again. This happens over and over again during the contraction phase. It's not one movement, it's many movements to kind of pull it all into the center. For relaxation, we have to get rid of the calcium. The calcium is pumped. That means, yep, more ATP back into the sarcoplasmic reticulum. It's going up its gradient. So it's going to come off the troponin because that's an allosteric. There's no bond here. So it's easy for it to come off the troponin, pumped back into the sarcoplasmic reticulum. When it comes off the troponin, the tropomyosin moves back to block the binding site, and the myosin cannot stick to the actin anymore. So the actin moves back to the resting point by something called elastic recoil. So what do we have here? We have one twitch. One twitch is one contraction, one relaxation. And the best example of a single twitch is blinking your eyes. Your eyes blink, that's one contraction, relaxation. Most action potentials or most muscle actions are more than one twitch. It takes more, but we see that we have the contraction phase is always faster than relaxation. Contraction takes less time. The latent period is the time between the action potential and the contraction phase. So we actually have a latent period. I redrew it in. I've kind of got it a little bit off, but the idea is latency is between action potential to the contraction. And that is the end of skeletal muscle part 3.